Sure. So hi everyone, my name is Tapaswini, and today I'm presenting my honors thesis, NeuroRule or rule-based neural network distillation. So this research focuses on bridging the gap between the high-performance capabilities of neural networks and the critical need for transparency in human-centric decision-making. So in modern deep learning, models often face a performance versus explainability trade-off. On one end, we have intrinsically interpretable models like shallow decision trees or sparse linear regressions. And these models are mathematically transparent, but they often lack the capacity to capture the high-dimensional nonlinearities typically required in the problem we're looking at. On the other hand, high-capacity models like deep neural networks, like AlexNet shown on screen, achieve state-of-the-art performance by learning complex representations across millions of parameters. However, they often operate as black box models or models that are inherently uninterpretable to a human. In high stakes environments like clinical diagnostics, a medical professional needs to know more than just a single output classification. They require a set of persistent, auditable logical steps that remain consistent across an entire patient population.
Awesome. Could you turn your volume up, just like your verbal volume? You're at the edge of what I don't have the best hearing and I'm having trouble following what you're saying.
Sure. So to address this black box problem, the current industry standards are post hoc local explanation methods like LIME and SHAP. However, these methods do not attempt to understand the entire model, and instead they focus on per instance explanations. While powerful for individual classifications, these methods are limited by global inconsistency. A local explanation for one input point doesn't provide enough information on how the model behaves across the entire input distribution. This can often lead to trustworthiness problems in real-world environments. This research proposes a solution to address this gap, a knowledge distillation framework that results in globally explainable Boolean rule sets from neural network targets. Adapting the evoder symbolic infrastructure, this research treats neural networks as targets for the evolution process, distilling the black box model performance into minimal sets of logic expressions. While traditional distillation focuses on model compression or transferring knowledge from a heavy teacher network to a smaller student network to improve inference speed, this project uses it to transfer the higher performance capabilities of a neural network to a more interpretable one. In this pipeline, the pre-trained neural network acts as the target object, which means that the rule sets are trained to match the output distribution of the neural networks rather than the ground truth data. The neural network has already mapped the complex high-dimensional input space into a more structured latent space. Thus, the rule sets can capture a more generalized version of the logic than if they were trained on the ground truth data alone. So using discrete symbolic rules can introduce challenges when training in traditional ML settings. Standard machine learning relies on stochastic gradient descent, which requires the models to be differentiable. However, logic rule sets are composed of discrete conditional statements that are inherently non-differentiable. Furthermore, finding the optimal rule set is a combinatorial problem with an exponentially large search space. As a result, evolutionary algorithms are uniquely suited for the search landscape. By using a population-based search, evolution can explore multiple logical structures at the same time. Additionally, it supports multi-objective optimization, which allows for the discovery of rule sets that perform well against two conflicting objectives, such as accuracy, or how well it mimics the black box neural network, and complexity, or the size of the resulting rule set. This allows the pipeline to produce a wide range of models, giving domain experts the choice between simpler, more interpretable models or complex, highly performant ones. As a result, there are three primary contributions. So first is an evolutionary method for distilling black box neural network models into explicit rule set models. Second is a method for making rule sets more explainable by including a brevity objective. And third is a demonstration that distillation is still viable even when the ground truth data used to create the target network isn't available. This research establishes that black box neural network models can be made explainable and therefore useful in real-world environments where trustworthiness is really important. We'll first look at some of the most common tools for model transparency, which include post hoc feature attribution methods like LIME and SHAP, followed by a framework that designs models that are transparent by design. So starting off, we have the LIME algorithm, which is a post hoc explanation algorithm useful for explaining a single prediction output. LIME operates by slightly perturbing an input data point to see how the model's prediction changes across these various perturbations. It then fits a basic regression model to these perturbations to explain the specific decision. One drawback is that Lime can often be unstable, as small changes in how the perturbations are applied can lead to vastly different explanations, even if the input point is exactly the same. SHAP, or Shapley additive explanations, is grounded in game theory concepts. Each feature is assigned an importance value on how much the feature contributed to the final outcome. While SHAP is more stable than Lime, it is fundamentally still a local tool that doesn't give too much insight on the global logic of the model. While Lime and SHAP are useful for local insights, their instability and lack of global logic highlights a need for models that are transparent by design. One example is eVoter, a framework that evolves rule sets based on extended propositional logic expressions. The primary advantage of the eVoter grammar is its ability to discover human-readable logic that behaves similarly to black box models. Because the rules are expressed in standard propositional logic, they provide direct insight into the model's behavior and can make hidden biases explicit. Furthermore, the symbolic nature of eVoter allows for human-in-the-loop interventions, so unlike neural weights, these rules can be directly edited by domain experts to remove any identified biases or to add additional constraints as necessary. Previous applications of eVoter have shown success in both prediction and policy search, but there is a lack of research on how integrating the black box network and additional search objectives in the evolution process can influence performance. Building on the theoretical foundations of these past works is central to the methodology of NeuroRule. This work follows a similar evolution process, but with a focus on explainability. So NeuroRule uses the rule set grammar and evolution algorithms proposed in eVoter with a new fitness function and distillation pipeline. So the propositional logic framework established in eVoter is used to represent the model behavior and subsequent evolution optimization. So a rule set is defined as a collection of n discrete rules structured as a set of disjoint conditional statements. Each specific rule then follows a standard structure consisting of feature comparisons and a resulting action. This form results in a linear list structure that allows for concise conditionals. A condition within a rule set compares an input feature value against a constant threshold or another input feature value. The framework also supports linear coefficients, power expressions, and comparison operators to model nonlinear relationships. When an input vector is passed through the rule set, the conditions are evaluated in sequence. So each triggered rule proposes an action, or in this case, a classification label, and an associated coefficient. The final prediction is then the action with the highest cumulative coefficient value. Each set also includes a default rule, which acts as the logical else statement. It typically captures the most common class label. The rule set models are passed through specialized genetic algorithms to create new rule sets each generation. Each algorithm can be classified as either a crossover algorithm or a mutation algorithm. So crossover algorithms operate at the rule set level. There are 3 crossover strategies used. So first is single point crossover, which combines parent rule sets at randomly selected crossover points. Next, we have uniform crossover, which randomly samples rules from parent rule sets to create the new rule set. And then finally, we have combined rules crossover, which merges conditions and rules together that share the same action. So mutation algorithms apply changes at different granularities within a rule set. So there are 3 levels of mutations possible. At the condition level, mutations consist of changes in the feature threshold, relational operators, and linear coefficients. At the rule level, mutations consist of adding, removing, or modifying specific combinations of the conditions. And at the rule set level, mutations consist of changes on the entire rule architecture. So this includes adding, removing, or reordering the rules themselves. To improve search efficiency, the framework also includes a heuristic to reject any mutations that result in a redundancy, such as age is less than 15 and less than 20, or a contradiction, such as age is less than 15 and greater than 30. While the eVoter grammar defines the structure of the rule set models, the direction of the evolution optimization is directed by optimization objectives and their corresponding fitness functions. For the purpose of distillation, the fitness function here focuses selection primarily on the maximization of predictive accuracy. So given a set of n data points and a black box model S, the accuracy fitness is the accuracy fitness for a rule set is defined as the proportion of correct classifications. So essentially, the predictive accuracy is calculated against the black box model. The core of the methodology is the distillation pipeline, which basically facilitates the transfer of knowledge from the black box model to the interpretable one. So the full distillation pipeline is shown here on screen. The process begins with a population of rule sets that use the evoder grammar, and in each generation, the candidate models undergo crossover and mutation as described earlier. The resulting new rule sets are then passed through the fitness function, and their performance is evaluated against the black box model through the accuracy metric we saw earlier. The rule sets are then sorted by their fitness scores, and the top N individuals are selected to persist on to the next generation. And over successive generations, the iterative loop basically allows the rule set to internalize the logic of the neural network. To validate the efficacy of symbolic distillation, experimentation uses 3 medical classification datasets from the UC Irvine collection. These benchmarks were specifically chosen because clinical diagnostics represents a high-stakes domain where the black box nature of neural networks is still a significant barrier to adoption. So first we have Breast Cancer Wisconsin, which diagnoses patients on features derived from the images of cell masses and nuclei. Second is Heart Failure Prediction, which diagnoses patients on the risk of heart disease based on clinical information. And third is Diabetes Health Indicators, which is a large-scale data set that diagnoses patients based on lifestyle information. In these environments, prediction is not nearly enough, as clinicians require the transparent steps that a distilled rule set provides for medical accountability. To investigate the relationship between data availability and model robustness, a tiered data partitioning strategy was implemented. So the dataset is essentially categorized into in-distribution middle data and out-of-distribution tail data. The neural network is trained across 3 distinct data ratios, in this case, 80%, 90%, 90%, and 95%. In the 90% case, for example, the model trains on the central mass of the distribution, while the extreme 5% on both sides is reserved for out-of-distribution testing. This structure serves 2 primary functions. First is sample efficiency analysis, as it observes how the evolutionary search scales as training volume increases in the central mass of the distribution. And second is extrapolation stress testing, as it measures the performance drop-off when the rule set is forced to extrapolate to unseen data. Experimentation uses the following target network from which rule sets attempt to distill knowledge from. So the neural network is implemented as a multi-layer perceptron with a funnel-shaped architecture to promote feature abstraction. The design utilizes a structural bottleneck with decreasing hidden layer sizes and a final softmax output to discretize the outputs into binary class labels. This architectural design basically allows the evolutionary algorithm to optimize against a simple neural network, providing a consistent fitness signal to prevent premature convergence and local optima. Finally, the rule set evolution setup is consistent between the baseline evoder models and the experimental NeuroRule models. The baseline models optimize directly against the ground truth clinical data labels, providing the baseline results for analysis. And in the experimental configuration, the distillation pipeline basically replaces the ground truth labels with the outputs of the neural network. The evolution hyperparameters include a high mutation probability of 0.7 and a novelty multiplier of 1.5. And this high rate of exploration is stabilized through the MLP, which provides a consistent fitness signal that prevents premature convergence. So the experimental results are classified into 2 primary dimensions, in-distribution interpolation and out-of-distribution extrapolation. This distillation process is intended to guide the evolutionary search towards the underlying structure of the data. So we're basically looking for comparable performance on the known and unknown data distributions. Regarding the in-distribution performance, results show that the network-evolved rule sets yield a slight improvement in both accuracy and variance compared to the ground truth baseline. As seen with the diabetes health indicators data sets here in the 90 and 95% interval experiments, the network-evolved rule set generally performed better than the baseline rule set, which is shown in blue. So the experimental is green, baseline is blue. The neural network likely acts as a smoother function for the rule sets to approximate, and this effect basically provides the evolutionary algorithm with a more continuous fitness landscape preventing the search from being trapped in local optima defined by individual outliers. The resulting rule set model is then able to model the behavior of the neural target, combining the generalizable insights from the rule set with the higher performance of the neural network.
Clarification. So the accuracy here is accuracy with respect to like the final label or the exact outputs of the target neural network?
This is the final label, so the ground truth data.
Okay, so these are all binary classification tasks.
It's like 2 or 3 labels per data set.
2 or 3. Do you know what like the accuracy would be if you just go with the training data distribution and just like always guess the most common class?
So no baseline.
Well, it's a different kind of baseline. So like, let's say you had a data set where it's 99% label A and 1% label B. If you always just blindly output label A, you get 99% accuracy. So anytime you're reporting accuracy, a key thing is like, what can you do? What's the best you can do knowing the label distribution in the training data, but not knowing anything about the actual input features in the training data?
Yeah, so the data sets are pretty much evenly distributed between all 3 classes or 2 classes. So I think the biggest discrepancy I saw was a 40% to 60% like class distribution for like the outputs. So it's like pretty evenly split.
Okay.
So these experiments also reveal a cost to the explainable model in comparison to the MLP accuracy, which is shown in red at the top. This accuracy ceiling suggests a difference in model capacity. So the neural networks are characterized by a higher parameter density, which is why they likely achieve higher in-distribution accuracy by excelling at interpolation. In contrast, the rule sets don't have the same capacity to model such complicated relationships, and so they don't necessarily perform as well during interpolation. This result suggests that while MLPs are optimized for fitting known data distributions, the rule sets can at most approximate the behavior of the MLP. So the most critical findings appear in the out-of-distribution analysis, where the extrapolation capabilities of these rule sets was tested. While the neural network and baseline rule set achieve comparable performance within the training distribution, the rule sets evolved against the neural target consistently demonstrate higher robustness when presented with unseen data in the out-of-distribution tails. So these figures illustrate the out-of-distribution accuracy during the evolution process for the diabetes dataset. So plots A and B on the left side here demonstrate that the rule set evolution basically discovers symbolic logic that surpasses the neural baseline under moderate distribution shifts, so for the 80% and 90% cases. In the 95% data range, which is plot C on the right, the performance of the rule set network converges close to the MLP accuracy. These results suggest that the rule set is able to discover logic that remains robust beyond the in-distribution samples and allows for this higher performance on the out-of-distribution samples. So the slide shows an example rule set as a result of the distillation process. As expected, the rules follow reasonable comparisons where conditions that indicate higher blood pressure or low physical activity often correlate with the higher risk of diabetes. One thing to note is that the rule set itself is very big. This structure in particular has about 40 rules, with each rule consisting of 3 to 4 conditions. Such a structure would be really difficult for a domain expert to effectively parse and validate, which brings up the question of how we can make the rule sets be even more explainable. So addressing this issue requires revising the fitness function. Specifically, the new function should incorporate some metric that quantifies the size of the rule set model so that the distillation pipeline can aim to find solutions that maximize accuracy while minimizing the complexity of the final model. So one metric to do this is brevity, which is defined as the number of conditions in a given rule set. And in this new fitness function, brevity can be added as a minimization objective so that the evolutionary search is driven towards minimally sufficient logic that preserves performance while avoiding unnecessarily complex decision structures. As a result, the revised distillation pipeline, which in addition to performance, explicitly optimizes for explainability through this new brevity metric. So since there are 2 objectives now, the pipeline uses the NSGA2 algorithm, which is a multi-objective framework that selects models that perform well in at least one objective during the search process. So every generation results in a mix of models that are either really highly performing, really condensed, and ideally some models that are both high performing and condensed. So the analysis now turns to the results regarding the explainability pressure, specifically investigating whether the transition to human readable rule sets affects the overall model performance. Generally, adding the brevity objective results in little change in accuracy despite significant reductions in structural complexity. So the results demonstrate a significant functional similarity between the single objective and multi-objective evolved models. So as shown in the heart disease task here, the rule sets evolved with both accuracy and brevity, which are shown in green, almost entirely overlap with the unconstrained models, which are shown in blue. This suggests that the logic required to represent the neural networks, the behavior required to represent the neural network's behavior is pretty compact. So the rule sets end up being pretty compact. Furthermore, in several experiment intervals, brevity actually acted as a regularizer. So by explicitly limiting model capacity, the evolutionary search is forced to prioritize distribution invariant logic over training noise. So this results in models that are not only 50% smaller, but also more accurate than their more complex counterparts in some intervals. This effect is best visualized through a Pareto front, which is a graph of solutions plotted against two objectives to see the trade-off between accuracy, which is on the x-axis, and brevity, which is on the y-axis. In the scatter plot, the multi-objective solutions in green typically collapse toward the bottom horizontal axis, representing the optimal frontier where complexity cannot be reduced any further without losing accuracy. The overlap of markers on the far right of the x-axis indicates that the most accurate solutions are often among the most interpretable. This suggests that the search space can be successfully steered toward concise symbolic representations without falling into the local optima of overly complex heuristics. Finally, the inclusion of a brevity objective produced a dramatic reduction in accuracy variance. Across all clinical benchmarks in the multi-objective models, these models were significantly more stable, with variance reductions exceeding 90% in some cases. The brevity constraint essentially acts as a structural anchor, and by restricting the search space to more efficient rule sets, the optimization path becomes more predictable and less volatile. This stability makes these models particularly suitable for high-stakes deployment where reliability and clarity are as important as raw accuracy. So here's an example from the multi-objective experiments. The structure on the right is the entire model, which consists of only 3 rules and only a few conditions per rule. This demonstrates the efficacy of the distillation process where a complex neural network is reduced to the sparse symbolic representation without sacrificing the predictive power necessary to identify high or low risk factors. This simplification basically allows domain experts to parse and validate the final model a lot easier. So all of the experiments so far have made a critical assumption that the data used to train the target model is still available. However, this may not always be the case. In data agnostic scenarios, such as in proprietary or sensitive data experiments, the original training data may no longer be available. This brings up the question, is it possible to perform distillation of a target neural network without access to this ground truth data? To investigate the robustness of this framework in a data agnostic scenario, the data preparation is extended to a configuration where only the trained black box model is available. Essentially, the neural network is used to create a model sampled dataset to act as the training data for the rule set models. So the input points are randomly generated according to the upper and lower bounds of the original training set, and the output labels are generated by querying the black box model. This setup basically allows evolution to capture the structural logic of the neural target through the distillation pipeline, as well as a distributional sampling of the target model through this synthetic data process. Under this sample data setup, the results...
Wait, can you say, you might have said this, what kind of random distribution are you?
We're using a uniform distribution for simplicity. I'll mention this in the limitations later on as well.
How are you getting the ranges?
So the assumption is we have some problem that we're trying to solve, and we have access to domain experts who can give us a reasonable expectation of what the range could be for a given feature value. So if you're talking about blood pressure or something, there's a certain range that you would expect values to fall into.
Yeah.
So under this sample data setup, the results showed that despite a slight decrease in accuracy compared to the ground truth evolved rule sets, the sampling strategy still remains as a viable method in data agnostic scenarios. Particularly in the in-distribution case, results indicate a slight decrease in accuracy compared to the pure data baseline. So in configurations where evolution was performed exclusively on the target network sampled data, the rule sets consistently underperformed the models trained on the real labels. As shown in the graphs here for the diabetes dataset, the synthetic data evolved rule set, shown in green, generally converged below the baseline rule set, which is shown in blue. This performance decay suggests that the neural target contains some hallucinated decision boundaries in higher dimensional regions where the training data was originally sparse. Despite this gap in performance, these experiments still show practical application. So many experiment intervals demonstrated that rule set models that achieve classification accuracy, they basically achieve classification accuracy that is highly similar or like very similar to the target network, particularly in the out of distribution cases. So this basically demonstrates that even in a black box only environment, symbolic distillation can still successfully extract a logic set from a black box model.
The baseline here is NeuroRule.
NeuroRule trained with the ground truth data. So there are a few directions for future research to address some of the limitations of this work. So one of these directions includes testing with different data sets, and in particular, testing with varying feature distributions, types of variables, and the size of the data set to see how effective the distillation process is. Another direction includes hyperparameter tuning of the evolution process. So future work can investigate whether increasing the population sizes or implementing other mutation operators can facilitate better solution discovery, particularly in higher dimensional spaces. And finally, another direction includes applying the distillation framework to more complex deep learning architectures. So further testing involving different activation functions, neural network depth, or additional model classes such as transformers could determine if rule set distillation still remains as effective, regardless of the underlying black box complexity. So validating these methods across varied architectures ensures the framework's readiness for real-world applications, particularly in highly regulated industries such as healthcare, finance, and autonomous systems, where model transparency is an important requirement for safety and compliance. So ultimately, the NeuroRule framework demonstrates that the perceived gap between black box performance and human-level explainability can be bridged through symbolic distillation. The results show that symbolic models can achieve more than just interpretability. The three main contributions consist of an evolutionary method for distilling black box models into rule sets, a method for making rule sets more explainable by introducing a brevity objective, and a demonstration that distillation is still viable even without the ground truth data. This research shows that concise, stable, and verifiable rule sets can be extracted from complex neural teachers, even in data-restricted environments. By evolving human-readable logic from neural network behavior, such a framework can ensure that high-performance systems are both accurate and auditable, which is necessary for the deployment of artificial intelligence in high-stakes real-world environments. Thank you for listening.